Here on Earth, it seems like most things behave in a relatively similar way. If you throw a baseball up in the air, it will come back down. If you hit the ball with a bat, it'll go flying in the direction of your swing. For a long time, people didn't think too much about why these things happened. Theories were proposed, but none seemed quite right. That is, until Isaac Newton came into the picture.
Newton was born in England in 1643 and was by all standards a brilliant man. Besides independently inventing calculus, which changed the course of both mathematics and physics, Newton gave the world its first set of laws which accurately described the motion of objects in the universe.
In 1687, Newton published what would come to be known as the most influential work in the history of physics. Philosophiae Naturalis Principia Mathematica, or Principia for short. In this collection of 3 books, Newton demonstrated and proved his laws of motion and gravitation. Principia gained popularity quickly, and jump-started a scientific revolution that had been begun by Copernicus, Kepler, and Galileo.
So what was everyone so excited about? How could Principia be so earth-shattering to the entire scientific community? To better understand this question, we'll first have to learn about the laws Newton actually discovered. The first 3 laws we will discuss are known as Newton's laws of motion.
The first law states that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Essentially, if something is moving, but not speeding up or slowing down, it'll stay like that until something pushes against it or pulls it. This tendency for objects to maintain their speed and direction is commonly referred to as inertia. However, inertia is not the law, it's just a property of matter. So now let's look at an example of Newton's first law.
This is a picture of Voyager 1, an interstellar space probe launched by NASA in 1977. Besides a little bit of assist from the gravity of the planets it passed by, this spacecraft has been flying out towards the edge of the solar system at an average speed of about 16 kilometers every second since it launched 35 years ago. It hasn't had to propel itself in any way because there is nothing to slow it down. It will maintain its speed indefinitely, just as the first law predicts, until some force acts on it.
Newton's second law of motion states that the relationship between an object's mass, m, and its acceleration, a, and the applied force, F, is F equals m times a. 2 important ideas can be seen in this simple equation. The first is that increasing the mass of an object means you need more applied force to accelerate it. The second idea is that increasing the force applied to an object will increase its acceleration. Though these concepts seem simple, this little equation can actually be used to solve very many real-world problems. Here's an example.
This man here is trying to push what appears to be a very heavy scale model of the Earth. The object is so massive that the force he is applying is not nearly enough to accelerate it to any noticeable speed. However, if he got his friends to push with him and added some force, they could probably move it. If we knew the mass of this Earth and the force his friends applied, we could find out the acceleration using F equals m times a.
Newton's third law of motion states that for every action, there is an equal and opposite reaction. This law seems very simple, and that's because it is. Let's look at a case you and George Clooney might have both experienced.
When George Clooney fires his rifle, his shoulder will experience a force pushing against it from the front. This is commonly known as recoil, and it is caused by the force of the bullet leaving the barrel. As the bullet forces against the back of the barrel to propel itself forward, the gun itself experiences an equal and opposite force, pushing the gun back into Mr. Clooney's shoulder. Everywhere you find a force pushing or pulling, there is an equal and opposite force somewhere very close by. This is the last of Newton's laws of motion.
The fourth law that Newton described in Principia is the law of universal gravitation. It states that every mass in the universe attracts every other mass with a force that is directly proportional to the product of their masses, and inversely proportional to the distance between them. The fact that you aren't floating up out of your chair right now is evidence that this is true on Earth. But the idea that it was true everywhere in the universe was revolutionary. Let's look at the actual equation to understand this better.
Any two objects in the universe, in this case m1 and m2, are attracted to each other by the force of gravity. We can see from the equation that as the distance between them, represented by r, increases, the force of gravity between the objects will decrease. This is why you don't feel very much attraction to Pluto right now. Similarly, if we increase either of the masses of our two objects, the gravitational force between them will increase. This is precisely the reason a 20-pound weight is more difficult to lift than a 5-pound weight. The greater mass of the 20-pound weight means that it experiences greater attraction to the Earth due to gravity. Gravity is acting everywhere all the time, and we can use this equation to find out many interesting things in the universe. Newton, for example, used it to analyze the movements of the planets.
So now you know the four most influential laws in the history of physics. But why, besides their practical uses, were they so important? The answer can be found in the concepts of prediction and determinism. To understand how well Newton's laws apply to the real world, we'll first witness a simple demonstration of the second law of motion. Notice that the ping pong ball accelerates faster than the pool ball behind it when the force is transferred. This is due to the constraints of the equation F equals m times a. Clearly, Newton's laws are very applicable on this simple pool table. So if we have these laws that can predict the motion of objects when forces are acting on them, we should be able to predict the outcomes of different physical scenarios. For example, if a single pool ball is hit with the cue, we should be able to determine some things about its motion. We'd have to know a lot of different information, such as the mass of the ball, the force of the pool cue, the friction present between the ball and the surface of the pool table, air resistance, and so on. But given exact values for all those different variables, we could predict precisely the path, the velocity, and the acceleration of the ball at any point in its travel across the pool table. But what if we had more balls? Could we still predict what's going to happen when the white ball collides with the formation of balls at the other end of the table? The answer again is yes. As long as we have enough data about our pool table, the pool balls, the cue, and the environment, we could say what's going to happen to every single one of the balls on this table. But what about things that don't seem to follow the simple rules? What about humans? Broken down to its biological and neurological foundations, the brain is an extremely complex computer that takes a vast range of inputs and generates outputs in response. If we could discover what rules the brain used to compute its outputs, could we predict the actions of humans as well? These were exactly the questions being asked in the wake of Newton's discovery. Philosophers questioned the idea of free will, and many began to adopt a deterministic viewpoint, the idea that everything happens according to laws, and there is only one possible future for the universe. Unfortunately for these philosophers, a new discovery came along in the 20th century that completely destroyed the conventional ideas of determinism and predictability. That something was quantum mechanics. We'll have to wait for part 2 to learn about that.